Hello everyone, welcome to this LeetCode daily coding where we are going to go through power of 4. So basically here you receive as input an integer n and we are supposed to return true or false depending on if the input we receive is a power of 4 or not. So let's say you receive as input n equal to 16. 16 is actually equal to 4 power of 2. So 16 is actually a power of 4. 5 is not a power of 4 because you can't represent 5 with the representation 4 power of something. And then 1 is actually a power of 4. Why? Because 1 is equal to 4 power of 0. So this is the constraint. Now the question is, how do we solve it? We have some example. We know what we are expecting from us. How do we solve it? So in this video we are going to see two approaches where we are going to elaborate and explain exactly the thought process behind the approaches. So before diving into the various approaches, if you're new here, don't hesitate to subscribe to not miss what you're doing here, because here we are doing LeetCode daily hackering solution, everything related to data structure and algorithm. So if you're interested in any of those topics, you are highly recommend to subscribe. So let us dive in our first approach. Our first approach will basically be the brute force approach. What does that mean? We want a number to be the power of 4, right? 4 power of an integer. So we are going to think of it this way. If you are a value of 4 power of integer, that means you are a consecutive representation of 4 times 4 times 4 times 4. For instance, the first one we were having was 16, right? 16 was 4 power of 2, which is actually equal of 4 times 4, right? So basically, given that, you know that if the number is actually a representation of 4, 4, 4, 4, you can just loop through, you can keep dividing the number by 4 until you reach 1. And if you are able to still have a multiple of 4 while you are dividing, that means yes, you are going to end up with a number which is a power of 4. So how can you represent that? So that can be easily represented by, say, if n is actually equal to 0, you return false first, because it's actually edge case. You don't want to live here because this loop is never going to catch this scenario. Now you are going to have your loop saying that while n is actually different from 1, you check if that n is actually not a multiple of 4, you return false. Otherwise, you apply the division and then you come back. So with a number like 16, how will it look like? So with 16, you are going to make the first check. Is actually n different from 1? Yes. Is actually n modulo 4 different from 0? No, it's actually equal to 0. So this is going to divide n. So after the first iteration, is going to be 4. After the second iteration is going to be 1. And then here we are going to return. That is why this is actually working. So if we submit this, you are going to see that it is working perfectly. Now, that being said, you see it is working perfectly. Now, that being said, how can we approach it differently? This is actually already performing well. Before diving into the second approach, this program is actually bigger of 1. Why is it bigger of 1? Because despite the fact that we have a while loop here, we know that the while loop cannot exceed 2 power of 15. It cannot exceed 15 operation. Why? Because our limit is saying that we have 2 power of 31 minus 1, right? Which is actually less than 2 power of 16. Are we okay? Sorry. Which is less than 2 power of 32. Which is less than 2 power of, 2 power of 2 times 16, sorry, 2 power of, let me erase this, 2 power of 2 times 16. which is less than 4 power of 16. So this is what I'm multiplying to give the 4. So less than 4 power of 16. And if it's less than 4 power of 15, 4 power of 16, that means the number of iterations we are going to make to have and the value is actually less than 50, less than 16. That is why I'm claiming that this algorithm is actually performing with a maximum number of iteration of 15. That is why it's big of 1. And the space complexity is actually big of 1. We are storing nothing. So now this was the first approach. Now what about the second approach? The second approach now is related to bit operation. So we are going to leverage the fact that a power of 2 is actually equal to 2 power of 2n. That means a power of 4 is actually a power of 2 where the power is actually an even number. So for us to achieve that, we are going to make sure that the number is first a positive integer, the number is a power of 2, and that power of 2 is even. So those are the 3 checks we are going to perform here. How will the code look like? So this is the code we are going to use for that. So n is actually greater than 0, yes. To check if the number is positive, directly you can just check if n is actually greater than 0. This is the basic check to check that the number is positive. Now to check if the number is a power of 2, we need to check if the number contains only 1 and 0, because power of 2 are represented in bit operation by 1 and 0. That is why you have 4 is equal to 1 0 0, 2 is equal to 1 0, 8 is equal to 1 and 3 0. So basically a power of 2 is actually a representation of 1 and just 0 at the end. And how will you make sure that an integer is actually a power of 2? To make sure that an integer is a power of 2, you just take an operator with that integer and the integer minus 1. Why? Because an integer minus 1, if the element is a power of 2, let's say maybe this one, the representation of this minus 1 will actually be 1 1. So the representation of this minus 1 is actually an integer or a bit representation with only 1s, with a number of bits less than this one. So it's going to, this minus 1 is going to give you 11. And then if you make an operator between this and this, eventually you are going to have 0. Why? Because 1 and 0 is actually 0, 1 and 0 is actually 0, and the 0 and 1 is actually 0. So basically if you are able to have n and n minus 1 which is equal to 0, then it's a power of 2. So that's why I'm checking here. If n and n minus 1 is equal to 0, then it's a power of 2. And the last check is actually checking if the power of 2 is actually even. Why am I doing that? So what is my approach of checking that the power of 2 is even? So we know that we know that at this point we already have a power of 2, right? Which can be something like this, which can be something, anything like this, but we know that we have 1 and 0 0 0 0. So now the first thing you need to ask yourself, what is the difference between a power of 2 which is even and the power of 2 which is not even? It's basic the number of 1 we have here, right? So the idea is to take another binary representation that will help us to figure out it easily. So the idea is to have a representation of a number which is like this. Let me take another color, which is like this: 1 0 1 0 1 0 1 0 and so on. So basically we are checking an integer which has this representation. Why? Because we know that if you have an integer with this representation, an operator explicit operator of that integer, and our n will actually give us that n. Will actually give us n. Why am I saying that? Let's say you have this one 100. If you have that good. If I'm having, let me erase this, I'm going to understand it better. Let's have this 100. What will happen is that the 1 will actually match this one, and then this one is going to be 1, and since we have 0 0 0 here, it's going to erase everything, and we are just going to have 0 0 here. So you just need to have a representation where the number of the various ones are actually placed on odd position, because if they are placed on odd position, you are sure that by making the AND operator with the power of 2, if the result is actually that element, that means it is actually an even power of 2. Whereas if you take an integer, if you take something like this, if you take a bit representation like this, which is not the power of 2, because this is actually 8, it is not the power of 4. If you take the AND operator, the 1 will actually be tied to a 0, which will end up giving you 0 instead of n. So we are going to leverage that to check if the input is actually even power of 2, and we are just going to take the biggest representation of n in this frame, in the frame of 2 power of 31, which is represented like this 1 0 1 0 1 0, and that value is actually this value. So that is where this one is coming from. So basically, if you run this, you are going to see that it's actually also performing well. So these are my approaches of solving this. I hope you do enjoy it. Feel free to leave me any input. I'll be really happy to interact with you regarding this. See you on the next video. Ciao.